Um, I'm Steve Bourne. I'm from Atkins, as Stan said. I'm a project director in our North America office, and I am the R&D chair of the North American office. My background's actually in water resources engineering. I am not a Gator, but I am a Yellow Jacket, so I feel a certain kinship through our rivalry with Georgia. University of Georgia, right? Yeah, we love you guys. Anyway, the work that I do, like the background is in water resources engineering, but I actually do software development a lot of the time. Mostly developing software for water resources engineers, and you know, I'm now branching out into lots of other areas in civil engineering. So, making data fun was not the title of my talk. I think Stan assigned me that title. So I'm hoping that by virtue of the fact that we're talking about big data, it's going to be fun. But I also added and valuable, because that's really what the focus is. Part of my first interaction with Stan was to come up with an idea for an app. Stan didn't actually ask me to do that, I just did it anyway, because I develop iOS apps. The idea was, let's make an app where you can go to the ocean and stand at the water's edge and make a record of that's where the water is. Why would we do that? Well, firstly, it's so that I can take my wife on dates. That's her feet, by the way, and those are my feet. But the larger picture is that we would get a record of sea level rise. Like, imagine if everyone was doing that for the last 30 years. We would get a pretty good picture of sea level rise. And what's interesting about this app idea is that it really brings out all the issues of big data. Big data is kind of anathema to us in the science field, because as someone was saying yesterday, you know, we're focused on systems and understanding the mechanics of things. And big data is really about just record everything that you see and figure it out later. So, you know, this app in and of itself brings out that idea. If you're a cartographer, if you're a hydraulician, if you're a fluid mechanics person, if you're a CFD modeler, all the fields that you can think of, you have real problems with this app. Because, you know, think about it. You know, think about if you're a cartographer, you have to think about which datum are you using. You know, you're making a record of where the sea level is. Well, what datum? What is zero? You know, if you're thinking about fluid mechanics, what tide level are you at? You know, if you're thinking about kind of any field that you think about, this is going to cause big problems. You know, how do you work out this data? This data would be incredibly noisy if we actually recorded it. But in the world of big data, you record it anyway. And so that's kind of the start of this talk. I'd like to thank Stan for inviting me to do this, because it let me do some research on big data and understand what big data is about. Someone mentioned yesterday the V's of big data. There's actually, it started out with 3 from a guy named Doug Laney at Gartner back in 2001. And he defined volume, velocity, variety. That's what big data is about. Those are the dimensions that you have to worry about. And lately, they've added veracity to it. Is the data that you're recording true? How true is it? How precise is it? How accurate is it? Volume, like I said, don't sample, just observe. So, you know, the idea is that, you know, if something is happening, record it. That's the big data idea. Velocity, the spigot problem is what it's called. You know, there is a massive stream of data occurring at all times, and you are going to run into problems if you think about, you know, actually recording that and storing it. Variety, text, images, video, audio, all of that. All of it is big data, all of it needs to be recorded. When you get into video, I mean, think about the volumes. You know, what does YouTube have to deal with? It's a massive amount of data that you're talking about. And then, you know, veracity, question the truth. Is what you're recording actually true? Is it a measure of what you're trying to record? So I went further into big data. I wanted to find out, you know, what are we talking about here? This is a diagram of what we call prefix multipliers. prefix, so you put kilo, mega, giga, tera, peta, exa, zeta, yada, that was a new one for me, in front of byte, and that's when you start talking about, the size of data. Kilo is 2 to the power of 10. Mega is 2 to the power of 20. They roughly match up with 1,000, a million, a billion, a trillion, and so on. But that is really the measure of data. Where is big data? I don't know if anyone calls it small data, but that's what I'm doing. Basically, out to about the giga level, that's the stuff you can keep on your own PC. That's the stuff you can work with on your PC. Past that is what we call big data. You can't actually feasibly work on a big data set on a single PC. It would take you too long to process it. It's the kind of thing where, it takes you 1.5 years to process 1 year of data. If you do that, you'll waste your whole career. You'll never actually get to an answer. And so you need to parallelize. You need to bring in lots of cores, lots of computing power to work with big data. Here's some examples. These were fascinating. I wish I could do more of these. Your standard smartphone has about 32 gigabytes, 64 gigabytes, so you can see where that lands on this scale. The next one is 3 petabytes. That's the Library of Congress. The next one is 32 petabytes. That's the storage in NASA's Center for Climate Simulation. If you keep going, you get to the Hadron Collider. 200 petabytes, that's the annual storage from the Large Hadron Collider. So everything that there are sensing in the collider makes up about 200 petabytes per year. What's interesting is that's about 1/1000th of 1% of what is actually being sensed in the Hadron Collider. They have to, that's the spigot problem. They have to kind of ignore a lot of it. Go out further, you get to Facebook. So Facebook has more storage than the Large Hadron Collider. 300 petabytes, that's Facebook's data warehouse. And then if you keep going, and this is what I found the most fascinating, 667 exabytes is the amount of data that's actually transmitted in the world every year. So imagine how many libraries of Congress are transmitted every year across the world. Here's an example of the veracity problem. How big is the Library of Congress? There are blogs and blogs and pages about whether you can use the Library of Congress as a unit of measure of big data. And the brackets that I have up there give the range of how big the Library of Congress is according to different people. So the lower end there is about 15 terabytes. The higher end, 3 petabytes. And it just depends on which part of the libraries you're including. Like there are digital stacks in the libraries. If you include those, you get to the petabyte level. If you just include the text, it's the terabyte level. So no one really knows how big the Library of Congress is. And so, a lot of people try to use it as a unit of measure of big data. The truth is you can't really do that. So what about environmental science? What's big data in environmental science? Did more research on this and included some of the sources that I've been using throughout my career. There is a real-time deforestation watch. That's the World Resources Institute is doing that. So in real time, they're tracking how much deforestation is occurring across the globe. Citizen science, this is from Oxford University. That is a network. It's not really a single study. It's a network for people to actually add algorithms to work on big data. Encyclopedia of Life. This is a database that has a record of every single species known to man. I think there are about 2 million of them. And there's pages, there's observations of those species, there's history of those species, all of that. GCMs and downscaled models, I'll get into that a little bit later. I think we talked about that yesterday. Those are big data. That's the whole globe being modeled on an hourly time step for centuries, 500 years, that kind of thing. Quasi is the let me see if I can get this, a consortium of universities for the advancement of, oh, I spelled it wrong, for the advancement of hydrologic sciences incorporated. That is an agency that's been around for, I guess, about 10 years now, and their mission is to store water data. And they have done a really good job of creating standards, of creating a network, a federated network of servers that have water data around the world. Lots of good stuff there. The federal government is big into collecting data, national elevation data set, national hydrography data set. These are all data sets that have been created over the last 10 years and are getting more and more detailed and bigger and bigger. And then something that myself and Jack Hampson, who's in the audience from Atkins, is working on is the Open Water Data Initiative and the National Flood Interoperability Experiment. These are efforts going on right now to make data more open and open to scientists and make it possible for scientists to essentially donate their analytical capabilities to the big data problem. Given all that, it sounded like it was a lot of data, but compared to Facebook, compared to Google, compared to those efforts that are more in the commercial space, big data in environmental science still has a long way to go. This was a very short but kind of sweet quote that I found, trees can't tweet. It's true, people can, and so the big data sets in the commercial world are getting bigger and bigger. Trees can't do that, and so we have to put in a lot of effort to actually make big data happen in environmental science. We also need people. This is kind of an infamous quote from, this guy was the chief data scientist at Facebook. The best minds of my generation are thinking about how to make people click ads. That sucks. The millennials, you can't accuse them of being indirect. That really does suck. And I think that conferences like this are important to bring people out of that world and into the world of science. Okay, so what's the challenge? We've been talking about big data at this conference. We've been talking about big data for decades now, actually. What we have found is, this is called the value tree, data, information, knowledge, wisdom. What we have found, the challenge is that using data to build knowledge, that's really the way to go. In big data, the kind of mindset is just record everything. But in our science world, we found that we have to really think about what wisdom do we want to gain, what knowledge do we want to gain before we decide which data to collect. And so actually the rest of this presentation is kind of about that. What applications have we been building at Atkins that think about that knowledge, think about those decisions we want to make, and which data have we collected to do it. Okay, so I think I have 4 examples of where we've used big data. Each one starts out with a page like this. So there's a little background section. There's a decision that needs to be made. These are decision support systems, so we focus a lot on which decision actually needs to be made with them. The stakeholders that are involved, the key engineering questions, and the key natural systems questions. North Slope Decision Support System was a project that we started in 2008. It was sponsored by the Department of Energy, US Department of Energy. It was, the partners that worked on it were University of Alaska, Fairbanks, ourselves, and Texas A&M University. The key decision is where should we build an ice road? On the North Slope of Alaska, it's an oil-rich environment, and oil companies want to explore. Basically, they do a lot of geotechnical work to figure out where they think oil is, and then they have to go out and actually drill for it and try to find it. The problem is that up there it's a tundra environment, so it's environmentally sensitive. Also, there are endangered species up there. There are tribes up there with culturally important lands. So, it becomes a clash of stakeholders to do this oil exploration process. The only acceptable way to get across the tundra is to wait till winter and build an ice road. And so this tool was built for the stakeholders at that process to figure out where the best places to put ice roads are. It's not an analysis that a single person can do. It actually has to be a consensus among these stakeholders. And so this tool was built to bring transparency to that process. Key engineering questions: how much does the road cost? That's what the oil firms are interested in. How long do we have to build it? Does it avoid sensitive environmental areas? Does it avoid cultural resources? The key natural systems questions are impact on Arctic lakes under climate change. The material to actually build the road is from lakes on the North Slope. And so, under climate change, what they found is that the season to actually use the water from those lakes, when it's cold enough, has gone from 200 days per year to 100 days per year in the last 30 years. And so, understanding where are the lakes, how much water do they have, what species are in them that we might affect, how long are we going to have to actually pull that water from the lake and build the road, all important questions that this tool tried to address. In terms of big data, the NSDSS was a North Slope decision support system. It was really a variety issue. We needed a lot of different data sets: topography, transportation, endangered species, tribal lands, lake bathymetry, species within the lake, meteorology, general circulation models, regulatory buffers. That's just a few of them. We had to bring all that together to actually answer this question. The folks from Texas A&M, we told them, all right, come up with the best way to actually find the ideal ice road route. They came up with ant colony optimization to do that. Apparently, ants are very good at finding the most efficient route under lots of different constraints. And so the tool actually employs ant colony optimization with all those different data sets I talked about to find the ideal route. Avoiding polar bear dens, avoiding environmentally sensitive areas, keeping the cost minimized, keeping the safety maximized. This was the routine that we used to do that. Another interesting thing we did with the data was suggestive lake climate change impact modeling. The challenge, this is kind of our mission statement: automatically create a water budget model and a dissolved oxygen model for any lake on the landscape with a climate change forecast involved. So there's 15,000 lakes in our database covering the North Slope. We wanted to be able to click on any of those lakes and automatically create a water budget model for it and a DO model for it. And we actually created a routine that does this. We introduced a module called the semantic modeler. So we were kind of thinking bigger in terms of what type of model can use. A semantic modeler actually can implement lots of different models. It sort of interprets what you mean by a model and pulls the data to actually create the model automatically. We had a really good process here for working with the universities. We actually, we're not the modelers at Atkins. The universities are coming up with a way to do water budget modeling in the Arctic. And so we said, just write that down in a white paper and we will code it. And it turned out to be a really good way to do it. Rather than ask the researchers to write the code, they would just describe what model they wanted and we would write the code and put it into our semantic modeler. The modeler pulls from data sets, from big data sets, GCM-based projections for the climate forecast. From the university's meteorological data set, we pull historic weather. And because it's a semantic modeler, it actually ties into lots of different databases and can pull data in a suggestive process for modeling. Making polar bears fuzzy, this was another issue. This is actually an interesting issue in terms of big data, because what we were doing was increasing the, increasing the veracity. We were decreasing the veracity on purpose. There are databases from an organization called GBIF from the Encyclopedia of Life that has precise observations of polar bears. So if you actually use that data set, you can go out to the North Slope and have a pretty good chance of actually running into a polar bear. what we decided was we don't actually want to put that online as information because there's poachers of polar bears. And so what we actually had to do was introduce something called a fuzzer, which converts the data from precise observations to probabilities and coarsens it accordingly. So there you have an issue of actually decreasing the veracity of the data. You have much more precise observations than you want to let out there. That was an interesting process. Okay, the next presentation is about Stormcaster. Stormcaster came out of the North Slope Decision Support System. In that process, we actually built a server of GCM data. GCM data is big data. And actually getting that data for a particular part of the world is difficult. It was difficult at the time. This was 2008. The data that comes out of GCMs is in a binary format. It's difficult to read. And so we created a service, essentially, that you know, any tool can tap into and say, I want a GCM projection for this part of the world, and it just feeds it out as standard ASCII data. So what we built from it was a tool called Stormcaster, and what this is an online tool that anyone can access, atkinsstormcaster.com, and you can go to your town and kind of pick a historic rain gauge there, and it will give you a forecast of how your 100-year storm is going to change over the next 100 years. What we found, actually, when we looked at some research from NOAA, was that the assumption that we often use that a 100-year storm, the storm that will occur with 1% probability, the assumption that we take is that that's staying the same through time. It's stationary. Stationarity is dead, and this is a perfect example of it. It's actually changing over time. What we can see in these two charts here is the last 50 years, or at the time, the last 50 years, 1958 to 2008. This was published by NOAA. And the map on the left shows the percentage change in annual rainfall across the United States. So the southeast is getting drier. The northeast is getting wetter. This is not projections. This is not models. This isn't UN IPCC. This is actually recorded historic data. And so you can see that, you know, the 100-year storm, that assumption is wrong. You know, it is changing. And, you know, the chart on the left actually goes to the extreme events and shows the increases in the amounts of very heavy precipitation over that same time period. You can see in the northeast, that's actually increased. You know, essentially the 100-year storm has increased by 67% over the last 50 years. And so what we wanted was a tool that looked at how is the 100-year storm going to change as we move into the future using the GCM projections. And so this is a single slide that describes the algorithm that was developed. I'm not really going to go into too much detail on what the algorithm is. That requires a longer presentation. But essentially, the tool in the end allows you to pick any city in the United States and produce this forecast. The example that you see on the right there is for Atlanta, and what it shows is that Atlanta precipitation for the 100-year storm is going to increase about 20% by 2050. And so if you're FEMA, if you're GEMA, Georgia Emergency Management Agency, if you're Atlanta, if you're the other cities around Atlanta, you need to be worried about that because the floodplains are changing and increasing accordingly. One of the topics we talked about yesterday was, okay, we're sharing a lot of data. How do we share analysis? How do we make it possible for people to provide their analytical brain power to others? How do we share that? One of the things that we're doing with Stormcaster is we're creating the Stormcaster network. The algorithm that we developed for downscaling GCMs and making that forecast, it works in some places, it doesn't work in others. You know, in the desert Southwest, for instance, that algorithm's not going to work that well. And so we're creating an ability to actually submit your algorithm for creating a forecast that will use the big data and produce the result for you. Here's another example, transportation planning in the UK. We at Atkins, we're kind of the engineer of record for the M25, which is the loop that goes around London. the freeway. And one of our charges for that is to come up with, in transportation modeling, you come up with a trip matrix, is what it's called. And this basically just defines all the different destinations that you can go to, and defines how often trips are made from one destination to another. Traditionally, what we've done with that is we do surveys. Basically, you stop people on the side of the road and ask them where they're going. You know, that causes lots of problems. Chief among them is that you are increasing congestion in the highway that you're trying to decrease congestion for. But you're also introducing a lot of bias in that process. And so recently, we made a partnership with one of the larger cell phone companies, does about 40% of the cell phones in the United Kingdom. And we are using their data, what they call breadcrumb data, which is, you know, every time you use your cell phone, you know, pull up a map, or anytime you're sharing location information, that information's going somewhere. And in the US, it's going to Google most of the time. And you can use that information to figure out, you know, where people are traveling. And so we have introduced a lot of new algorithms that use this spigot of big cell phone data to do our travel matrices. The issues that pop up with that with that exercise are velocity and privacy. You know, the big issue, it was interesting, I was talking to people from the UK about this, and they said, you know, the thing that we're worried about is The Guardian, the newspaper in the UK. We're not worried about being sued. You know, we don't care really, I mean, they care about it, but it's definitely a lower priority. We are worried about press, bad press for using that data. And so, you know, people are worried about, you know, how do you, basically Big Brother keeping track of where they are. And so there are a lot of measures in place that anonymize that data, that aggregate it, that bring it to a point where you really can't track it down to the individual. And that's a big issue in big data. And then of course there's the velocity problem and the spigot problem of 1.2 billion events per month. That's with 4G. When we go to 5G and start introducing Internet of Things, where the cell phones are actually communicating with, you know, your coffee maker, to tell it to make coffee because I'm coming home, that data is going to explode. And actually bringing all that data into, you know, we have a tap essentially of all of that data. We have to record it, aggregate it, throw it away a lot. There are big algorithms in place to do that. Another example is growth forecasting. This is for Atlanta. We have a population forecasting tool that essentially, it'll take a regional projection from an econometric model, and it'll disaggregate it down to what's called the TAZ level, traffic analysis zone level. So it's taking, you know, Atlanta's gonna go from 6 million people to 10 million people over the next 40 years. It's taking that data and saying exactly where those people will be over time. You know, allocating new houses, new commercial buildings, new parcels. There are 22 million acres in the Atlanta regional area, and it's modeling every single acre over time. How does it do that? How does it know where things are going to be built? This is called a likelihood raster that it uses. It essentially uses expressways, major roads, commercial land uses, other factors that are geographically based to produce a likelihood of development over time. And it allocates new growth to, according to this likelihood raster. I have an animation here. I hope it's working. This is the result of the model. You can see Atlanta growing. I think this one goes out to 2020. Yellow is residential, and red is commercial. And so, you know, this is definitely a big data issue. We're working with lots of data to make this happen. Okay, so those were examples of things we've done in the past, and now I'm going to get into what we're doing now. Silos are dead, especially analysis ones. This is a statement that has a veracity problem. It's not true. Silos are still very much alive in terms of data, in terms of analysis. We, in our industry, we are transportation engineers, water resources engineers. planners, population projection scientists, we're in silos. The data that we have is in silos. The analysis that we do is in silos. And so silos are dead is an untrue statement. But we are going in a direction where we're trying to make that true. We're trying to join all that together. And the way that we're doing that is a new initiative we're calling Future-Proofing Cities. It's been around for a little while now. We first focused on the developing world in it, India, places in the Far East. And what its focus is on building resiliency in cities. I'm actually the North American leader of Future-Proofing Cities for Atkins. And we are crafting for the developed world a method for understanding resiliency in cities and for building resiliency. The process is, it's very stakeholder oriented. Essentially, you start on the left with your stakeholders and your team of experts, and you develop master plans for your city, scenarios of how you'd like to build resiliency in your cities. And then in the center there, that's where all the Atkins experts come together, and our partners, and we do something called stress testing, where we take your master plans, which traditionally master plans are a city planning exercise. They're kind of aspirational. The city doesn't actually know that they can create the city that they're coming up with their plan. It's sort of like what we'd like to do. We're introducing the stress testing process that models the population growth within the city, models climate change as it's occurring and affecting the city, models sea level rise as it's occurring and affecting the city, and other disasters as well. And we are evaluating whether these master plans will actually work or not, in a very quantitative, very realistic way. We do that for an extended period, basically working with external drivers to the city, simulation model that we're developing right now, and measuring the city in terms of how well it's doing under the master plan. And then we take all of that back to the stakeholders, and we build consensus on which master plan they actually want to go with. So, it's a very sort of a next generation of master planning process that we're developing right now. Community stress testing, this is kind of how it works. The bad community is the red line, the good community is the green line. Or put it another way, the less resilient community is the red line, the more resilient community is the green line. And we are literally modeling the city over this time span. We're going from 2015 to 2050, actually. And we are modeling business as usual in the city as the population grows, as the economy grows, and we're also modeling disasters as they hit the city. One of our first examples that we're working on is the Dominican Republic, different cities in the Dominican Republic under a USAID grant. And the disaster of concern there is tropical storms, quite like Florida. And so, this simulation model is actually modeling those storms as they hit the city and destroy houses and buildings, and how the recovery of that occurs on a building by building basis to evaluate the resiliency of the city. We do that for a base case, like the current infrastructure for the city, and then we do it with the master plan, where they've introduced things like seawalls and other measures to counteract climate change. And we evaluate how effective those are going to be. Stress testing, so this is another illustration of the process. You have multiple master plans, they all go into the stress test, and at the far end, you get a result, which compares the different master plans and calculates with those box plots the uncertainty in the analysis that we're doing. Okay, that's it. But one other thing, we actually have a display over there that has some of the Future-Proofing Cities products that we've been producing. There's a report card that we do for a city at the beginning of the process that looks at, how well the city is growing, what the economy is like, how vulnerable it is to climate change and sea level rise. There's some products over there that you're welcome to take. Okay, that's it for me. Any questions?
We've got some time for questions for Steve. I'm gonna just
ask him a question on, there are quite a few, not quite a few, but I think we're going to be one of the first ones with a citizens sea level rise type application with the Seymour app. Can you, how much, one person standing on the water and pushing the button and recording where sea level is at that second is nonsense. You kind of understand that. But a million people doing it, then all of a sudden you get some things that you can work with. I know that you developed this for Apple, or we're working with the Apple concept. Would it be hard to get it onto Android and the other systems?
Not at all.
Okay.
Yeah, there are ways to you develop it once actually, and it ports it out to the different platforms.
Okay.
Yeah.
All right. So this is. Are there many of those around?
Not that I know of.
Yeah, I think this is going to be one.
Researchers trying to come up with an app idea. You go to the App Store, make sure no one's done it, and I didn't see anything like that.
Yeah, I think we're one of the first ones to have.
Steve, the NOAA study that shows rainfall is only decreasing trend in South Florida. Be very careful about using that. The reason is the GCM, general situation model, the grid size is very big, 50 kilometer by 50 kilometer. There's a very active area of research on trying to downscale those models to localize weather pattern. And what we have seen in South Florida is it's very hard to look at those GCM results and just stick to them. It's that veracity part that you brought up. It's very critical. There's people that are doing this research trying to downscale those models. One example is sea breeze has a major impact on rainfall pattern on the coast. And some of those sea breeze dynamics cannot be captured in 50 kilometer by 50 kilometer grid. We look at that NOAA study, give us some ideas, but we take it with a grain of salt, understanding that we got to look at localized phenomena a lot carefully before we actually.
Right. Well, I mean, something to pay attention to is that NOAA study is historical data. It doesn't have anything to do with GCMs. It's just rainfall recorded over 1958 to 2008. Right. And then in terms of the GCM stuff, that's a big field, and they're doing really good stuff actually at South Florida to do the downscaling that you're talking about. If you have a GCM, most GCMs have about a 3-degree latitude, longitude grid cell size. So 2 of them cover Florida, that kind of thing. And so the projections that you get out of those GCMs are highly biased. And you can't really say, okay, this is how rainfall is going to change in Florida, on a absolute level. But you can pay attention to the trends in the GCMs. And so, the algorithm that we have does that. It basically applies those trends to historical rainfall patterns. Even doing that, I mean, if you talk to Obi at South Florida, he'll say that's not a good model either. You actually need a mechanistic model of rainfall in South Florida to really understand the physics of rainfall and how it's changing. So yeah, I agree, absolutely. There's a lot of uncertainty in that data. And what we've taken is essentially the trends that the GCMs are projecting and just use those. And in fact, we're actually using 12 different GCMs, which are all saying different things about those trends and producing an ensemble to get best case, worst case scenario.